solar thermometers. So, thank you. Yes, and indeed, thank you very much to the organizers for the opportunity to present our work, which actually appeared on the archive on Friday. And yeah, also thank you to all of you for sticking around. I'm aware that I'm the only thing standing between you and a Florentine steak, but yeah, so I'll try to keep in time and show you a little bit about well, how to use Axions as solar thermometers. So, I mean, during this workshop, we have and we will hear quite a bit about helioscopes. So I just wanted to give a very naive and simple explanation of what they are. So if you think about the sun as basically a thermal bath, then you can create axions inside the sun. And since they are not very, I mean, they are weakly interacting, they can basically leave the sun unperturbed. And then once they reach Earth, you can set up a nice opaque tube with a magnetic field inside, where they can hopefully reconvert into X-rays that you can then observe. And so if you basically track the movement of the sun with X-ray detectors and X-ray optics, that's basically the hope of these helioscopes to detect axions. And last week, for those who were around, Esther gave an overview talk about the detectors for the next generation of helioscope. And on Friday, I believe Julia will talk about IAXO in more detail. So I will just leave you with this very phenomenologist-like description of helioscopes. And just maybe tell you why you should really care about them and why they are quite interesting. So one thing that has already been mentioned in this workshop is that they place indeed one of the strongest bounds on the interaction of axions with photons for basically a very broad mass range. So basically for masses below some few milli-electron volts, you have this very nice bound from the CAST experiment. And keep in mind this number, so milli-electron volt range, because it's going to be relevant a bit later on. And yeah, again, on Friday, we'll hear more about the great physics you can do with the IAXO. So I just want to highlight that apart from being sensitive to realistic QCD IAXO models, if you get lucky, you can not just detect a signal, but you can also measure not just the mass, not just the coupling, but also the mass of these particles. And in principle, also, you could use them as a way to distinguish different axion models and to study things like, for example, macroscopic magnetic fields inside the sun, which are otherwise very, very difficult to study. So, if axions exist, then really this would be a great opportunity, not just for particle physics, but also for astrophysics or solar astrophysics in this case. And there are a couple of things you need to do to understand what you are seeing if you see a signal. And the theory part of this is to figure out what the sort of interactions are that you expect for axions inside the sun. And so this is something that my collaborators and I, so Jörg Jeckel and Lennart Thorman, who are also co-authors on the study that I'm going to get to in the second part of this talk, did some time ago, is to revisit basically all these computations. And basically, yeah, so what you see here is the different types of interactions that can take place if axions are coupled to photons or electrons. And also Lennart and others did some follow-up work on the nucleon interactions. But basically, for one kind of simplifying assumption that you can make for at least the current generation of helioscopes is that you can basically ignore for the sort of production part the axion mass, because as I said, you're not sensitive to axions above the masses of a few milli-electron volt, and the temperature of the sun is kilo-electron volt. And so basically, for all practical intents and purposes, I mean, we calculate the precision of this approximation or the accuracy of this, but you can just pretend that axions are massless for what the production is concerned. And what I will focus on in this talk is basically the Primakov, which for KSVZ type axion models is the dominant interaction in the sun. And basically, due to the spectral information that you have in principle, you can a posteriori after detection verify that indeed this is the type of axion you've seen. So, but for now, I'm just going to discuss Primakov axions only, or Primakov axions where Primakov interaction is the dominant interaction. And if you do that, then basically you can, for example, using the code that we've put out, compute the spectral and spatial distribution of the Primakov flux on the solar disk that you see on the sky, effectively. And basically you can see that, you know, the vast majority, as you would expect, of the axion flux that you see and observe is produced in the sort of inner parts of the sun. And then what we also did is we, since we had this code, you know, you can also make a survey of all the solar models that we have available. Oh, sorry. And what we found in this previous study is basically that there were a couple of solar models where, which also have been used in, you know, relatively recent studies, where actually not all the information is available or not tracked in these solar models. And you can see that especially for the axion-electron interaction here, there's this discrepancy between the predicted flux for the axion-electron interactions, and also a smaller discrepancy between the Primakov interactions for sort of these solar models that don't include this information and others that do. So yeah, one conclusion is to basically not use these models. And then as we've also heard earlier today, there is the solar abundance or solar metallicity problem, which appears because, well, at least in the past, you had basically two classes of solar models, some that can explain or are in agreement with the helioseismological measurements, and others that are in agreement with measurements in the solar photosphere. And so basically what we did here is to take or to use Monte Carlo examples of these solar models for the two sort of representative classes, and to compute the expectation value for the flux. And so you can see here that indeed the solar metallicity problem manifests itself in a systematic shift between these different classes of models for the axion photon and the axion electron interactions. And we also looked at the sort of statistical uncertainties that you get from basically Monte Carloing all these uncertainties that enter in the solar model computations. And so here is a sort of the summary and takeaways that basically you should really stick to the sort of more recent solar models where all the element abundances are tracked and you get more accurate predictions for your flux. And as you can see here, if you look at the solar metallicity problem or at the different solar models, then you get, you know, a percent level sort of systematic uncertainty, but that can be a bit higher for specific energy ranges. And also another important thing is to consider is the sort of opacity, axion opacity that you assume. And there, similarly, we looked at different predictions or different theoretical codes that calculate this. And there it's also on average a very small effect, but really if you want to study in a sort of very futuristic scenario, say the Iron Peak or something like that in a solar model when you detect an axion, then you need to be really careful because there are huge discrepancies. And anyway, I mean, the sort of takeaway message here is that the statistical uncertainty that you get from different solar models is much smaller, or is smaller at least than the systematic effects. So this is in some sense good news because it means that you can use the axion as a messenger particle in the sense that you don't have a lot of statistical uncertainty, but it's also good news for theorists in the sense that, you know, systematic is something you can in principle improve by better computation and also by, for example, trying to solve the solar abundance problem, which would make this systematic go away. And indeed, I wouldn't say that this is a settled issue yet, but here's a paper that I wanted to highlight where a recent newer generation of solar models or the sort of abundances claims to be consistent with both helioseismological and photospheric measurements. So maybe, you know, this is one systematic uncertainty that might disappear in the future. And, you know, as I said, small statistics means that you can use axions as messengers. And so this is a plot from a previous study where people showed that you can make a detection not only of the axion, but to really distinguish the the axion that you see from an axion that is effectively massless. So basically inside these blue regions, which sort of, depending on the energy resolution your detector has in YAXO, you can detect both mass and coupling of the axion with, I think it was a 3 sigma, yes, significance. And so what we did is to look at KSVZ type models with one additional new heavy fermion to try and see if we can learn a bit more than just the mass and coupling. And because these are sort of discrete models, you have some separation in your parameter space, and you can basically use this to distinguish, in this assumption at least, you can solve sort of the solar metallicity problem. You can at least get a hint for deciding which model is correct. Now, of course, we only looked at this particular case with one additional new heavy fermion. So you might want to ask yourself the question, well, okay, but you can only do this in this case. If you had, in principle, a more complicated KSVZ model, then you can't do this anymore. And so to this end, with a student of mine, a master student, we looked at how you can sort of assess this question, or about sort of just generally trying to catalog all KSVZ models. And that might sound like a daunting task, because you can add many new quarks. But actually, if you impose the phenomenological selection criteria for these preferred models, then what you find is that basically, as you add more and more of these heavy fermions, eventually you will induce a lambda pole at lower and lower energies. And if you set a threshold, say the Planck mass or something else that you find unacceptably low, then this will naturally limit the number of models. So with the sort of, for the choices that we made, which is Planck mass cutoff, you find that there's only a limited number of these KSVZ models that you can construct, and also a very limited number of E over N values, which is still too large sort of to make our claim work if you consider this scenario. But still, that was a very interesting exercise, which was also then picked up by another group who did the same thing for DFSZ models. Unfortunately, for these models, you don't have very strong selection criteria like for the KSVZ one. So you have to make some additional assumption, trust that your sampling is correct. But in principle, you can come up with a sort of distribution of E over N values. And if you include uncertainties from axion pion mixing, and also the running of the coupling, which has been recently, which has also been discussed at this workshop, then you can, we didn't include this bit, but basically already from this you can sort of define, you can sort of redefine the QCD axion band, and you can have a theoretical prior on your models, if you will. Now, from this sort of aside, let me get to the paper that I advertised at the start. And the sort of starting point of this idea is basically, well, one iteration of this figure. So what you see here is what the CAST collaboration did a while back, basically a simulation of an axion signal in the CAST detector. So, this is, they used an X-ray detector, a pixel-based photon counting detector, and you can see that you have, like 200 times 60 pixel here. I cut off a bit of the detector. But anyway, the basic idea is that you have this signal, and you basically produce with CAST an axion image of the sun, so to speak, right? It's not, you can see that there is some, it's not entirely spherically symmetric, but it's, pretty good when it comes to this. And also, you can see that you have detectors with a high number of pixels available. So basically, the idea is to, well, what could we do if we estimate the number of photon counts in basically rings about the center of this image and learn something about solar properties? So this is what every phenomenologist does. So basically, instead of taking this more realistic image, we take a spherically symmetric detector. This is our mock detector with like 16 and 16 pixels for illustration. Our real study, we did 128 times 128. And then also, these are 6 sort of rings that we drew around this detector, but in reality, it will be 20, as you will see later on the plot. But you can simulate the signal in IAXO that you would see on such a detector, or the equivalent one in our study, and you can basically ask yourself, how many photons did I see in these rings? And the reason why you want to choose a large number of pixels is because if you think about integrating, I mean, how do you estimate the number of photons contained in this ring? Well, you have to make some assumption about how the counts you observe are distributed in each pixel. And of course, the coarser the pixelation is, the more errors you will introduce from this assumption. We did the sort of boring thing of assuming an equal distribution, but of course, if you have many pixels, this doesn't matter so much. I mean, in our paper, we also quantified this a little bit. And so basically, the idea then is to, could you, you can obviously generate, say, 1,000 set of pseudo data for IAXO. How can you invert this image, or how you can use these counts that you estimate to learn something about solar model parameters? So let's look at the simplified equation for the Primakov rate. So basically, you have the axion photon coupling here. You have something called the Debye screening scale and the temperature. I mean, this is to some approximation the function that you have, which ignores electron degeneracy and a few other corrections that we talk about in our previous paper. And this, unfortunately, I will have to come back a bit later because it actually does matter at some point. But for now, you can use this, or you can take this as a very good approximation of the Primakov rate. And you see that it only depends on this sort of global parameter, which is the axion photon coupling, and it depends on these local properties of the sun, which is T of R and the Debye scale of R. And of course, if you have two parameters and one quantity, or well, I mean 3 plus one T and one kappa parameter for each of your rings, how would you break this degeneracy? And of course, there is one more quantity that enters here, which is energy. And so basically, using this energy information, you can break the degeneracy between the parameters. So that's the sort of basic idea. So the number of counts, this is the expectation value of the number of counts, is basically proportional to the integral over the flux on the axion flux on the solar disk, which you can then project to Earth and then convert into photons that you observe, times basically this what we call the gamma bar parameter, so the energy averaged Primakov rate. And you can you can take as many energy bins as you want. We took 4 in the end because naturally you would expect that you need at least 3 bins because you have one global parameter and these local parameters, so you need 2 plus epsilon bins in some sense. Right. So the thing is, what we did in our paper is to make general polynomial ansatz for the energy average Primakov rates. But basically, I will just start with the easiest thing to demonstrate this, which is a piecewise constant. So basically, a step function approximation of these rates. So this is basically the quantity I showed before, and we take some piecewise constant function. Then you can just plug this into the integral, which is a bit annoying, but it's not a very difficult integral to solve, and you will end up with some expression which includes these coefficients, which contain information about T and kappa, and yeah, basically some quantity that involves your radial bins. And if you fix these radial bins, basically all you have to do is you have to only compute these coefficients once, and then you can use them over and over again. Because basically you can think of this as a matrix multiplication with a matrix of this form. And if you look at this for a bit longer, then you realize, okay, this is a upper triagonal matrix. So you can iteratively solve the whole system of equations, taking the average rate to be 0 at the outer edges of the sun, and then basically propagating inwards, solving this system of equation iteratively. And you can also propagate the errors. And so what you end up with is an expression for these coefficients and the errors, and then basically you can fit your temperature the temperature and the kappa parameters in this piecewise constant approximation. Now, this is all very pedagogical, I hope, and straightforward and analytically solvable, so that's nice. But of course, we want to have something that is not, that is a bit closer to the actual form of T of R and kappa of R. So what we tried is to take normal splines, but unfortunately this will introduce ringing. So basically you will get unphysical behavior of your interpolation. So you get values below 0. And also this this inversion of the matrix only works if you have, if the matrix is not singular. And this will basically, you will have to choose your bins in a way that ensure that you have at least one count in each one of them. And that will basically shift your bins all towards the center of the sun. So that's not what we want. So we want to take an approach with fixed bins and a general spline interpolation. And then basically you can do the same thing again, except that now, because it's some generic polynomial, you will end up with, a non-quadratic matrix, non-square matrix, so you can't solve this analytically. But of course, what you can do is you can do the forward fitting. You can calculate the matrix, and that basically gets rid of this annoying integration, which speeds up, your fitting procedure. And then you can just directly fit your parameters to the estimated photon count data in these rings that I was showing before. And if you do that, we did this for 2 benchmark cases. So one is basically just below the current cast limit. So that's 6 times 10 to the minus 11 inverse GeV. And then we took a case that is a bit lower, but that would, with the sort of current cast parameter, still result in a very strong detection of axions. I mean, we made a background-free approximation, but basically this is, this is some value of the coupling where you would still be able to claim a discovery. Anyway, so what you see here is that if you look at the red dots, that you can get a relatively, except for this central beam, which is basically due to a volume effect, you can get a very accurate reconstruction of the temperature in most of the sun, up to half of the radius. And for the stronger coupling, that even goes all the way up to almost all of the sort of interior of the sun. For kappa, that's not possible, which has to do with the weaker dependence on of the rates on kappa. I mean, the temperature goes in with the number of produced axions as T to the 6, whereas this is sort of a much weaker dependence. And I should just point out that at this coupling, you would expect 300,000 axion events. So that's a very strong statistic. So you actually start seeing the effect that you took, not the correct Primakov rate, but some approximation, because we computed this mock data with the actual, the actual data you would expect from the sun. Right, and the statistical errors of these, if you sort of look at the median errors in this region, are fairly good. So you can, with the amount of data we have, constrain the temperature dependence of, the radial dependence of the temperature quite well. Now, maybe one last sort of remark I wanted to make. Now you can say, okay, axions might not exist, and you've kind of done this study with things that don't exist. But how about neutrinos? Because phenomenologically speaking, neutrinos are fairly similar to axions, right? And I mean, it's been well known that there is such a thing as a neutrino image from these detectors. And I mean, we obviously thought about this, doing this. So can we do something similar with neutrinos? I mean, especially given that we considered 300,000 axions, and we have about 100,000 neutrino events in super K. So sounds about similar order of magnitude. Can you do something similar? We're not 100% sure that you can do it. I mean, we will definitely look into this a bit more in the future. But so this is basically the angular resolution. I mean, which you can also guess sort of from this image. So we have a huge PSF that we will have to take into account, which would dilute the statistical significance of your reconstruction. And also the recoil path of the electron is not aligned with, you know, unlike in the axion case where you have the path of the photon and the axion is identical. So there is this angle in between the two, which is basically reflecting this. So it's not clear to us from the literature. We didn't derive a definite conclusion if that's completely crazy or not, but at least it's something that is difficult, but we will continue to look into this and maybe see if there's something that can be done. So if you have ideas, of course, we are always very eager to discuss. Right, so as promised, I will not stop you from going for dinner eventually, but so just to sort of summarize the main points of what I was trying to get across today, is that we know the Primakov flux you know, relatively well at the percent level. We have a good handle on the accuracy of this approximation as well. And so basically, if we detect axions with the AXO or another helioscope, we can really do physics, astrophysics with axions. And in this talk, I hope that I could convince you that the solar axion image is very powerful in being able to tell us something about solar properties, namely in particular the reconstruction of the radial dependence of the temperature inside the sun. Of course, if you have many events, you should, you know, there are some computational complications involved that will make this a bit more expensive to estimate this and do these Monte Carlo simulations. But we, I mean, we checked that basically, if you put in what you, so if you use the approximated Primakov rate to do this whole exercise, you can, you know, more or less perfectly reconstruct both kappa and T. And in principle, you can also think about doing this with axion-electron interactions. The problem is, of course, that there are not just two main parameters that enter. So it's not just temperature and debye scale, but you will actually have to care about densities of of the different heavier elements inside the sun, and in theory of each individual ion that's present in the sun if you look at the peaks. So, you know, this can potentially become computationally very expensive to do a model independent reconstruction. Of course, if you make further assumptions like have been done in the past, you can you can certainly do this. And also, you know, as you saw at the beginning, so as you saw at the beginning, basically this is also part of this of my Marie Curie project, where one idea is to have this sort of growing base of different software codes, and so yeah, I think this project also nicely illustrates how we could build on the previous software package that we put out there to basically extend this and learn something about the radial dependence of the temperature inside the sun and use axions as solar thermometers. So with that, I'd like to close and ask for your questions. Thanks. Yeah.
Now questions.
Thank you for the talk. So in the axion case, is there any usefulness to looking at the axion-nucleon interactions?
Yes.
To produce fluxes from the sun?
So I mean,
you have proton-deuteron fusion gives you axions at MEV energies.
Mm-hmm.
CAST previously has done searches for this.
Yes.
I don't know if that gives you any extra information relative to just using the Primakov channel.
It would be a different coupling, right? So
it's a different coupling.
Of course, you can,
in terms of reconstructing solar parameters and things like that.
Yeah, no, we didn't think about this. I mean, usually the problem, but the challenge with this is that you know, if you want to look at the peaks or things like that, I mean, you need the energy resolution and you need to you need to be able to resolve these. So you need lots of events and but I mean, in principle, these peaks are very powerful. So I'm sure that something similar can be done, but we didn't think about this.
The downside of that might just be that because these processes are overwhelmingly taking place in the core, you're not necessarily going to get T of R.
Yeah.
Right. Similar to the neutrino case that you mentioned.
Yeah. So if the temperature, so if the power that the temperature enters into this is, you know, much higher than what we have here, then yes, this would be very focused to the inner regions. But, you know, you could see that, you know, even though, you know, at this point or at this point you have the majority of the flux, I mean, this obviously depends a little bit on our assumption of the interpolating function for the rates, right? But I mean, you due to continuity, and if you have, I mean, even if you have a few single events here, you can still learn something due to basically, well, the continuity of the functions, basically. Yeah. So you get a little bit of extra reach sort of from this. Yeah.
Okay, thanks.
Thanks for the talk. Going to the neutrino case, have you thought at all about hyper K? Because I guess you'll have more statistics. Do you know will it have the same angular resolution, or
so
with more angular resolution with enough statistics?
Yeah, I mean, statistics would definitely be very good. The angular resolution we didn't find. I mean, it is supposed to be better, but we didn't find too many concretes. Maybe we didn't. I mean, we now get in touch with the Super K collaboration to ask a bit more about specifics, because this is a very, you know, rather technical aspect that, yeah, if you don't do the experiment, maybe it's at least for us it was a bit difficult to make a guess. But in the literature, I didn't find too many concrete statements about how, I mean, how much better it will be. It's supposed to be better, but we at least didn't find anything.
More questions? From remote, I don't see anything. So probably we have a conclusion. So we thank Sebastian and all the speakers of the